Life is defined by boundaries, limits that hold us back, like fences, budgets, and laws. In science, too, there are limits, boundaries that matter cannot pass through. In thermodynamics, systems and their surroundings have clearly defined borders. There are two major types of systems, closed and open. In an open system, matter and energy can cross boundaries. In a boiling pot of water, energy is going into and coming out of the system, and gaseous water is also exiting the system. In a closed system, matter cannot cross boundaries, however energy can. When the lid's on it, the gaseous water cannot come out of it, yet energy is able to come into and out of the system. Now you have this energy that's being held in the system. So since the law of conservation states that energy can neither be created nor destroyed, any change in energy inside the system has to affect its surroundings.
For example, a fire will warm a room as the system gives off energy to the environment around it.
In thermodynamics, you'll often hear the term entropy. Entropy, scientifically, is a measure of how a system is progressing towards thermodynamic equilibrium. More easily, it's the disorder of the system. It is a state function, which means that it's solely dependent on its current state and doesn't matter about its past. So what do I mean by disordered? Think about something going from a solid to a gas. It's becoming more disordered since the molecules are all over the place now. But it's opposite. Think about it going from a liquid to a solid. It would have a negative entropy because it's becoming more ordered as it becomes more rigid.
Besides entropy, there's one other driving force for chemical reactions: enthalpy. It is a measure of the heat content of a chemical system and is represented by delta H. Basically, it is stored chemical energy that can be eventually used for a reaction. Now there are two types of reactions: endothermic and exothermic. Endothermic absorbs heat or light from their surroundings. Their products thus have more enthalpy than their reactants as it gains its energy that it absorbs. Think of when you sweat. The water that you sweat out absorbs the heat of your body to evaporate. It absorbs that energy. It thus has more enthalpy in its products. Its opposite is exothermic, in which it releases heat or light. Its reactants have more enthalpy than its products. Think of a lighter. In this, a reaction takes place in which it releases light, and with it, its energy. So how do these two relate? Together in an equation, they can be joined together to find Gibbs free energy. Gibbs free energy is the usable energy, the energy available to do work. The equation is change in free energy is equal to the change in enthalpy subtracting absolute temperature multiplied by entropy. A change in G less than 0 gives a spontaneous reaction. A change in G equals 0 is equilibrium. A change in G greater than 0 produces a non-spontaneous reaction. Now I know you're all like, hold up, what is a spontaneous reaction? What's a non-spontaneous reaction? Well, exactly what it sounds like. Think of a spontaneous. What are the first words that come to mind? Out of nowhere, suddenly, unpredictable. Spontaneous reactions are just that. They occur without being driven by an outside force. Its opposite is non-spontaneous. These require an outside source of energy to start up the reaction. A pencil rolling down an incline is an example of a spontaneous reaction, as there is no outside force that causes it to go down. However, if I have to push the pencil up the incline, that's a non-spontaneous reaction, as they are driven by an outside force. Now, all these reactions that we're talking about, they need to have a specific cause. What makes them go? This is activation energy. It's the amount of energy you have to put into a system for a chemical reaction to occur. And how is this created? Collisions. Collisions between molecules. However, these successful collisions are rare. You need a perfect amount of energy, and they need to hit each other head on perfectly so that you can get enough energy to create this reaction. The amount of activation energy needed determines the rate that these reactions can take place in. If a reaction needs a higher activation energy, it's going to take slower for it to happen because it needs all this extra energy. Most fuels burn at insignificant rates unless the activation energy needed is obtained through a spark. Once they burn, the reactions release enough energy so that they can happen.
Adenosine triphosphate, more commonly known as ATP, is the energy currency of the cell. It powers many life-sustaining reactions inside our bodies, like biosynthesis, contraction of muscles, ion movement. ATP is an important source of energy. The hydrolysis of ATP causes ADP to be formed. ADP is constantly broken apart to carry out many life processes. A third phosphate group is attached to ADP so it can regenerate into ATP again, creating this never-ending cycle.
A reverse reaction occurs when products revert to their reactants. When all these reactions are happening, forward and reverse, they will continue to happen in a cycle until it reaches chemical equilibrium. At equilibrium, the reaction does not end. It is simply happening in each direction at the same rate. At equilibrium, there's no net change, so the reactants are being formed just as the products are being formed.
Nature constantly tries to achieve equilibrium, however, it cannot be achieved. A system at equilibrium can do no work and therefore would die. Thermodynamics also tries to create an equilibrium state through energy coupling. In energy coupling, exergonic reactions, which release energy, are used to drive an endergonic reaction, which needs this energy. As a reaction proceeds to this equilibrium, the free energy of the mixture of reactants and products decreases, and that is thermodynamics.